Hi, this is Dave Ridyard. Welcome to our second Survey Design Express video. This time we're going to focus on a land survey in a rough terrain area. We've picked an area about 100 miles north of Los Angeles. It's certainly an area with a lot of geologic interest since the Garlock fault passes right through the middle of our survey area. Most of the survey area has fairly benign surface conditions, but the area to the northwest of the Garlock fault has some mountainous and very rugged terrain that we're going to have to be very careful with. You can also see Honda's performance testing track just to the east of the survey area. Before we go any further, I should just clarify that this video describes a hypothetical project and is for educational purposes only. No seismic project is planned in this area. We'll start off by doing a basic survey layout, and then we'll look briefly at the operational cost associated with the rough terrain. And then we'll look into some strategies to mitigate that cost and make the survey safer and less expensive to acquire. And finally, we'll look at some of the geophysical data quality considerations associated with our adjustments to the design to accommodate the mountainous terrain. This is the opening screen for the Tesseract software. Our first job is to create a new project for our survey design in the Garlock area. To give the project a little context, we'll start off by importing the outlines of all the cities in California. And as we zoom in, you can see that we're about 60 miles to the east of Bakersfield, just to the north of California City. Switching to a view of the topography, you can see that in addition to the mountainous area to the northwest, we're also going to have to deal with the major highways passing through the survey area. The first step in creating a new survey design in Tesseract is to run a wizard. Wizards are a really easy way to just step through everything that you need to do to create your project. In this case, we're going to use a land survey design wizard. The wizard allows you to enter all the necessary parameters to create the survey design. In this case, we've chosen to do a dynamite survey design using a 50-meter shot interval. In addition to parameters relating to the geometry of the survey, we're also going to allow you to enter a number of operational parameters affecting the cost of the survey. Later on, we'll be modifying these parameters so that we can look at the cost impact associated with the rough terrain. Also note that we've entered into Tesseract the fact that we have 3,000 channels available for this project. You'll see the importance of this in a few minutes. After entering all the necessary parameters into the wizard, Tesseract will go ahead and build the nominal geometry. In this case, a straightforward orthogonal grid. The next step is to set up a roll pattern, and once again we're going to go through a wizard that sets up the rolling sequence for our project. Before starting the survey layout exercise, we ran the geophysics wizard to calculate key geophysical parameters such as the minimum 3,000 meter offsets which are required to image our relatively shallow targets on this project. To meet this offset requirement, Tesseract has suggested a minimum live patch of 16 lines live, each with 120 channels. Tesseract now suggests to us how much efficiency could be gained by using a longer patch or a wider patch. Configurations requiring more than the 3,000 channels available to us on the crew are shown in red. In this case, we're just going to keep to the simple minimum patch, though if this was a real survey design, we'd certainly investigate the possible improvements in efficiency. Having designed the receivers for our patch, we must now set up the shots required for each patch. We can then visualize the roll sequence for any part of the patch, including the edges and corners. We can also calculate key operational parameters associated with the logistics of moving the patches. Now we can run our binning wizard to look at the subsurface sampling that we get from our survey. The user has great flexibility in setting up the binning grid, but typically the default parameters are those required to create the standard displays, such as fold, minimum offset, and maximum offset. Now we turn our attention to the operational issues associated with the area of rough terrain. We've drawn a boundary around the area where we think that operations will be affected by steep slopes. So we've selected all the receivers inside the rough terrain area, and we're going to change some key operational parameters for these receivers, such as the transit speed when we move from one receiver to the next, and the time to plant each receiver. Before applying these new settings, you can see that the time to acquire the survey is estimated at 14.9 days. After applying the new operational parameters to the receivers, you can see that we've added about 0.7 of a day to the total acquisition time. We now go through a similar process for the source points, and we find that we have added almost 2 days to the total time to acquire the survey. Let's look in more detail at what we can do to address the challenges of working in the rough terrain area. I'm going to start by importing a digital elevation model. This 30-meter data is the lowest resolution that's offered by Photosat. Much higher resolutions are available if required. Of course, the real challenge is not the elevation, it's the slope. So let's calculate slope maps for the area that we're working in. I'm now going to assume that slopes greater than 10 degrees will cause some reduction in our overall operational performance, and slopes 20 degrees or more are going to be considered unsafe to work in. You can see the valleys and ridges are aligned in a roughly northwest to southeast direction, fairly similar to our line direction. So what I'm going to do is I'm going to edit each receiver line such that it roughly follows the valley floor, thus avoiding the operational cost and safety issues associated with working in regions of steep slope. Since the source lines run generally orthogonal to the valleys, it's inevitable that some of our source points will fall in areas of steep slope. So we're going to take those that are in a dangerous area and simply kill them, so we won't acquire these source points. And finally, we're going to exclude any source point that lies within 100 meters of the road. After adapting our survey design to avoid the rough terrain areas, we now have to estimate the time to acquire the survey with this new geometry. Once again, we identify all the sources and receivers that lie within the steep slope area and adjust the operational parameters to reflect the extra effort associated with working in these difficult areas. This careful work has saved us about a day and a half of survey acquisition time. It's also made the project a lot safer. Now we're ready to look at the coverage of our target area. Notice that I'm going to do 2 sets of binning, one with the conventional flat earth binning, but I'm also going to apply the elevation model so that we can see if the elevation changes have made any significant difference to our coverage. As you might expect, the total fold looks good. Other than the natural limitations of the geometry, the long offset coverage is also as we would expect and as we would hope. The minimum offset coverage shows a few more problems, particularly in the areas where we've had to adapt our survey design to accommodate the terrain. Here we're looking at the short offset fold, and we see relatively little impact when we apply the correction for elevations. This is in part because we've moved as many sources and receivers as possible down into the valleys, so that they're roughly at the same elevation as the rest of the survey. We can look at the offset distribution for a row or column of bins, and we can look at the offset and azimuth distribution for a single bin or for a group of bins. Let's briefly review what we've done in this exercise. First of all, we developed a basic survey layout and we examined the operational cost of operating in a rough terrain area. Then we adapted our design to make the survey less expensive and safer to acquire. Then we checked that there were no significant adverse implications to the geophysical data quality of our project. So, with about 2 hours work, we were able to create this survey and then make it safer and less expensive to acquire. We hope you've enjoyed this video, and we hope you'll contact us soon to let us know what you think of it and what you'd like to see in the next one. Thanks for your attention. Goodbye for now.